Uh, and it made me think of this morning when I was coming in here, that I got this matrix on my shirt. And since we were talking about matrices, maybe I can try to explain it. So for those of you who can't clearly see, basically I have this math on my shirt. So and maybe I can try to explain it. Briefly. So I have this matrix on my shirt, and it looks like this. We'll call it M, and it's a 4x4 matrix, and it has this Jordan symbol. Yeah, we can talk about that, Michelle. I'll get to that in a second. So I have this shirt, and it has a symbol on it, and the symbols are these Jordan things, like these Jumpmans, whatever. And then it has a 1, a 0, a 0, and then it has a 0, and it has another Jumpman, drawing very poorly. And then it has a 0 and a 0, and then it has a 0, and then it has another Jumpman. I have them switched. It doesn't matter. This one's red, and then this one's red. And this is like a math nerd shirt because it's a play on words. So this type of matrix, in particular, these numbers, if underneath it has this equation, which is really not an equation, it's a polynomial. And this polynomial has a specific name. It's called a minimum polynomial. And so on the bottom, you see this, and you see this. So this is what's on my shirt. Of course, the actual shirt, the red and black are flipped, but it's irrelevant. Doesn't change anything. So students have asked me about this, and this is a good place where I can sort of explain what this is all about. So I alluded to the fact Monday, that matrices are, they're important for lots and lots of reasons. But one reason that you can appreciate at this point is they are a useful way for us to sort of try to solve a system of equations. So for example, this matrix that you see on the screen might be of use. It could be of use to solve a system of 4 equations with 4 unknowns, maybe, So again, you guys are mostly familiar with 2 equations and 2 unknowns. That's usually done in high school algebra class. Sometimes you might even do 3 equations and 3 unknowns. This matrix might be useful for solving 4 equations and 4 unknowns. Or some of you are also familiar with, Abdullah and I had this discussion this morning. Some of you know that matrices are used to talk about transforming things in the plane. Okay, enough of that. So if we go to the system of equations thing, and we think about what I said the other day about the following issue. So a matrix problem or a matrix equation might look like this. It might look like some matrix A times a vector and equals some other vector. So just to point out for those of you who aren't too familiar with this, this is an unknown vector. This B represents a known vector. And of course, A is some matrix. So I alluded to this fact yesterday, excuse me, I keep saying yesterday, Monday, that one way we might be able to solve this is if A is square and it has an inverse, we can multiply both sides by the inverse. So one idea to determine x is x equals A inverse times the vector B. The thing is this, even if it does work, it's not always effective, because as I alluded to again on Monday, computing matrix inverses, even if it exists, is a difficult thing to do. Not just for the human, it's difficult for a computer. It takes time. It takes work, quote unquote. So what we ask then is we ask, okay, maybe there's a better way. And one of the quote unquote better ways is to take a matrix and rewrite it in a simpler form that's equivalent. Now, the analogy you might be familiar with is like take the number 1/2. Well, you can write the number 1/2 in many different ways. 2/4, right? 3/6, 10/20. So think about a very elementary problem where you have to add two fractions. One of the things you learn as a kid that you can only add fractions if they have the same denominator. So what we often have to do is we have to rewrite a fraction so that it matches, its denominator is the same as another fraction, and we can combine them. So it turns out that many matrices can be written in simpler forms. And then when the matrix is in its simpler form, it's a lot easier for not just the human, but also the computer to calculate. Does that make sense, maybe? So the most ideal situation, as I alluded to on the homework, was if you can make your matrix look like it's diagonal. If you can rewrite your matrix, if you can do something to it so that it has zeros everywhere and numbers on the diagonal. For example, you saw in the homework that there's a real simple pattern for computing powers of those matrices. Now, the problem is that's not always the case. We can't always find a corresponding diagonal matrix. But what we can do is we can find what's called the Jordan form. Hence the play on words with my shirt, because this is the Jordan logo, the Jumpman. And the Jordan form of a matrix is this, where you have numbers down the diagonal and perhaps a 1 on the off diagonal and zeros everywhere else. Now, why is this useful? Well, as you would imagine, with all those zeros everywhere, it's easy to calculate with this matrix. It's not the same as calculating if there's numbers everywhere. Think about multiplying and powers. So this matrix M which I'll write it more mathematically now, 23, 1, 0, 0, 0, 23, 0, 0, 0, 0, 45, 1, and then 0, 0, 0, 45. So those jump men on my chest are representing numbers. So this guy is called, or is said to be, by the way, I'm not testing you on any of this, but people have asked, and that's what I'm telling you. But you can Google all about this if you'd like. It's said to be in normal or particularly Jordan form. And then the polynomial which I've denoted P sub m of lambda, which is x minus 23 quantity squared, times x minus 45 quantity squared, is called the minimal, or the minimum, well, let's say minimal, the minimal polynomial of m. Now, this is high-level math right here. You typically don't learn about this in undergraduate. Sometimes, I guess maybe some people do. But it's typically reserved for higher-level courses. You're not supposed to, Mackenzie, right now. I'm just going to show you an interesting fact. But it turns out that these Jordan forms are very, very useful. Now, how is this polynomial related to the matrix? Well, what's fascinating is we could take this polynomial, and instead of plugging a number into it, we can actually plug a matrix into it. And then we can ask, what happens when we plug this matrix into the polynomial? Now, of course, you might right away say, well, how can I plug, oh, by the way, this should not be x's. These should be, I'm using the variable lambda, so let me be a little more clear. Sorry for that. The variable was lambda. So the question then becomes, okay, why do we care, whatever? Well, the reason that I'm telling you right now, the only thing you need to care is that getting a matrix in its Jordan form has benefits. That's what you need to know. And one of the nice things about these Jordan forms is they play very nicely in polynomials. And that makes doing lots of calculations and lots of problem solving easy. So let's plug it in. Now, of course, you might say, well, how can I plug a matrix in? What is a matrix minus a number? Well, we don't want to think of it that way. When we write the number 23 in context, we mean the matrix, you know, if put it this way, how could we generalize the notion of 23 in terms of matrices? Well, one intuitive way to think about it is, okay, maybe it's the matrix that has 23s everywhere. But it turns out that's not the right way to do it. The right way to think about 23 as you think about it as 23 times the identity matrix. So in other words, that means it's 23s on the diagonal and 0 everywhere else. Then the rules of arithmetic have analogy. So real quickly, let's do that. So if we evaluate this minimal polynomial of m at m, so we get, this is going to be very scary, so we'll write it as m minus 23, but the correct way to think about this is times I, the identity matrix. And this is quantity squared. And then this is m minus 45 times I, the identity matrix. So now we can write this out in all its glory. This is scary looking, but nonetheless, we can do it. It's 23, 1, 0, 0, and then 0, 23, 0, 0, and then 0, 0, 45, 1, and then 0, 0, 0, 45. So we'll do this piece in detail. And then you're going to understand that the structure is very similar for this guy, so we won't have to write all that out. We'll get what happens. So this is not hard to do. What happens? Look what happens when you do this. It's quite beautiful. The 23s do what? Well, the 23s go away, so I'm left with 0, 1, 0, 0. Then I'm left with 0, 0, 0, 0. Now I'm left with 0 and then 0. What's 45 minus 23? What's that? 22, right? So that's 22 and then 1 and then 0, 0, 0, 22. So I have that squared. And then this is times, what's going to happen over here? Well, the opposite's going to happen. So when we subtract, when we do the subtraction, you're going to have 23 minus 45. Oh, by the way, okay, that's good. So here, the top two canceled because they're the match, and down here, they didn't cancel, right? So it's going to be flip-flopped up here. You're going to have 23 minus 45 is negative 22, 1, 0, 0. Then it's going to be 0, negative 22, 0, 0. Then it's going to be 0, 0, 0, 1, and then 0, 0, 0, 0. So you see there's a lot of the same structure here. Now, what's quite fascinating is if I square both of these matrices and then multiply them together, something quite fascinating happens. Now, in order to save time, what we can do is we can use a calculator to do this arithmetic for us. So what I'll do is I'll switch my screen to show you some stuff. So right now you should be seeing what's this computer. Oh, we're going to have to reload it. God forbid. Bear with me. We have lost what we wanted to share you. Someone has a question. All right, so again, I want to compute these two matrices. And again, for the sake of saving time, and also when I say this, I'm going to do it on a calculator, but if you want to learn any of this, what I would encourage you to do is do it on your own, verify it. What's cool is we can do this, technology helps us. So I am going to plug this in, and you're not going to see it. Well, those in here will see it right now, but you guys won't see it yet. How do I type a matrix into this software? It's pretty easy. You just do 0, and then you put 1, 0, 0. That's the first row. And then it's 0, 0, 0, 0 is the second row. And perhaps, and then 22's in the bottom. So let's look at this. Well, I lost it. So right now I'm plugging this into the computer. So I plug this into the computer. It won't make sense to you right now. I don't think. You have to probably ponder what I did and how it works. But there is, forgot something. Forgot a 1. This should be a 1. So now the matrix A is this 4x4 matrix. And if you backtrack to the previous page, you'll see that that is indeed what it was. Now, what I can do is I can now tell it what B is. I'll say what this matrix is, and then I'm going to compute this. So right now, anytime I hit the letter A, so for example, if I hit 2 times capital A, it thinks that capital A is that matrix. It's stored in there. So now I'm going to store B. So what is B? Well, B is the opposite in a sense, not the opposite, but there's some symmetries here. B has negative 22s up top, right? And then 2 1s. So let's say B equals, so it's negative 22, 0. Oh, excuse me, that's 1, 0, 0. That's the first row. Then the second row is I'm going to have trouble here. Hit the wrong button. It's mad at me. Negative 22, 1, 0, 0. First row. What's the next row? The next row would be 0, negative 22, 0, 0. Third row was 0, 0, 0, 1. And then the last row was 0, 0, 0, 0. Oh boy, what was it mad at? So there we go, negative 22, negative 22. So let's double check that that's correct. Looks correct, good. So now we can just ask ourselves, okay, let's compute. What is A times B times B? That's A squared times B squared, is it not? And then when I hit that, I get this magical thing. It's zeros everywhere. So if I go back here, this turns out to just be, after some calculations, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So there are lots of matrices, or at least there is the possibility that lots of matrices, if I plug them into that polynomial, it's going to spit out 0. But this matrix M that I wrote down is in the simplest form, in the sense of calculating with it. So again, I thought this was worth sharing. Maybe it stimulates your imagination. Maybe you go and Google Jordan form. I don't know. Maybe you get interested in wanting to learn what all this stuff is useful for. Or maybe you don't give a damn, in which case I'm not mad at you. But people always say, what's the shirt mean? And then you guys are at a place where you can sort of understand it. And if you're interested, you can go learn more about it. Does anybody have a comment or a question? It's also good practice for you to plug that matrix in and calculate all this by hand. Look, I'm not asking you to know what a Jordan form is in this class. What I am asking you to be able to do is do arithmetic with matrices. So there's good practice. So let me repeat that. What we just did, you are not required to do necessarily. No one's going to ask you what a Jordan form is. However, you being able to do these computations is a learning objective of this class. Do we understand that? So I'm trying to give you perspective of why someone might want to be able to do all this stuff. Anyhow, let's move on. And if anybody ever wants to talk about this stuff, I'd be happy to do it. It's quite cool, in my opinion. All right. So the next thing I want to say is, and Michelle, you brought this up. Well, actually, first, there's a couple comments. So 2 classes ago, and this was brought to my attention this morning. So I gave you a hint for homework 6. And there's a slight typo for number 1. So what I wrote in class, and you could check your notes, I wrote f of a equals this. When we really want f of b. So if you studied what I told you, this should make sense. If you don't care, that's fine as well. But the hint I gave you was sort of misleading because I wrote the wrong letter down. The set we should have been worried about was B, not A. I don't know if that'll make the problem any easier for you to understand, but it is a hard problem. And then the second comment is there will be a quiz, and it's due Friday. It is not hard. It's not hard. I repeat, it is not. If you understand the basic ideas of this week and last week, like what does countable mean? What does uncountable mean? I'm not asking you to prove if anything's countable on there, right? There's no proofs. It's literally, I think it's 5 questions. Let me double check. I think it's 5 questions, 2 points each, I believe. Yeah, it's 5 questions, 2 points each. There is one computation on, there's 5 of them. One of the 5 requires you to do calculations. The other 4 do not. They're just basic facts, true and falses about what we've talked about. So, you know, I'm not going to sit here and say it's easy because some of you will not get them all correct, and so you're mean, but it's not, it should not take you more than a few minutes to do. I gave you a 30-minute time frame. So, again, I don't think it's difficult. There's 5 questions. 4 are basically, do you understand basic definitions? And one of them is asking you to do a computation. So if that computation takes you 10 minutes, 15 minutes, you still have plenty of time. So let's write that down. There's 5 total questions. 4 require. Better way to say it, do not require proof or computation. So only one's going to require that you have to do some actual computation. So anyhow, I'll try to get that done by Friday. So let me repeat. I know everybody gets worked up on homework 6. Let me say this. The idea of countable and uncountable is heavy. It's deep. What you should understand, what do I think is important for you to understand, that there is a difference between countable and uncountable. If you're having trouble proving things are countable, that's okay. That's not the end of the world. But you should understand the difference between countable and uncountable. You should know examples. Like the integers are countable, the real numbers are not countable. Even if you can't prove it, you should understand what they mean. Do we get that? And you know, if I ask you if a set is countable, you should be able to tell me yes or no right away. For example, if I say the even numbers that are integers, you should say yes, countable. If I say the real numbers, you should say no, they're not countable. So, I mean, I can't say it any clearer. I don't know how else to say it, but I wouldn't stress about those things. Some of you will have to worry about them in other courses. Others will never hear from them again. That's another way to think about it. But I did point out to you that you should also realize that these things, they do have consequences in things like computer science. Countable and uncountable definitely do. For example, can we compute something? Can a task be done? Okay, anyhow, that might not even make sense to you right now. So let's truck back along. Does anybody have any other questions about the quiz or anything of that nature? We did homework 7 basically last class. So if you need any help with homework 7, please see those notes or watch the lecture, because we did all the questions, I believe. Well, not the exact one, but we did it. Okay, so it's time to get back to our what we sort of jumped into at the end of last class. So last class, we defined big O notation. So one reason we like this, and we're going to do some examples shortly. One reason this is useful is it allows us to quantify growth rates. So this has many uses, such as analyzing algorithms. So, if you've paid any attention to the news since April and March, you've heard these words, actually, maybe not in this specific context, but one of the things you heard by all the jabronis of the world when the pandemic started is, we have exponential growth. We have exponential growth. We need to flatten the curve. Let's flatten the curve. Most people say exponential growth. I don't think they understand what the hell they're saying, but they say it nonetheless. But the fact of the matter is, growth rates are different. If you look at how things trend, there's different sort of quote unquote speeds to how things go. And the abstraction of this is usually sort of introduced in math class. So you have things like polynomial growth. So let's look at some things that are familiar to you. So you often hear phrases such as polynomial growth, linear growth, exponential growth, log growth, etc. And these phrases come from the fact that we're using these adjectives based on our experience from studying certain functions. So if I go to the next page, you might remember what certain graphs look like. If I have, if I put things in a coordinate system, you have things like exponential growth. These are things that grow really, really, really fast. Something like y equals a to the power x. Then you have something like linear growth, which is just a straight line. Y equals mx plus b. You might have polynomial growth. Y equals a polynomial. You might have log growth. So the point is if you read these things from left to right, so there is a clear, at least even as I've drawn this, difference in steepness, how fast they grow. So again, we'd like to be able to quantify this, and we'd like to know which functions sort of are in which classification. And so the way we did that, or the way we do that is we define what's called big O notation. So one of the skills you need to be able to do is the following, and we're going to do some, and this tends to be tricky at first for many students. I don't know of a good way to help you get over that hurdle, but it's kind of like a steep learning curve for many reasons. So a skill we need to have. You need to be able to show a given function f of x is big O of g of x. For given f and g. And so it would not be a bad idea for us to remember what the sort of definition is for this. So what does it mean for this to happen? So this means, so f is big O of g if there are, or there is, however you want to say it. I guess the correct way of saying it is there are constants, which we usually denote C and K, with the absolute value of f being less than or equal to some constant C times the absolute value of G, when your input is larger than this K. So this is usually difficult for students to to get to the bottom of the first time. And we're going to try to show you how to do it. So does anybody have a question or a comment? By the way, there's an equivalent way we could define this. If you were to divide both sides of this by, say, g, think of what we're saying. We're saying that if you take, this is saying that if you let x get large and large, if you take the limit as x goes to infinity, then the ratio of f over g is a constant. That's what this says. That means they're growing at the same sort of place. So what I'm saying by that is the definition above is equivalent to saying that the limit as x goes to infinity of this thing is equal to or less than or equal to c. So that means if you think about it in terms of the graphs are behaving the same as x gets large. So the graphs have similar quote unquote behavior as x gets large. Or a better way to say that is x grows without bound. Okay, so here's what we need to do. Let's just jump right into an example, and you're going to have questions, and that's great. So I hope you ask them, because this is typically difficult at first. So number one, we want to show f of x equals, let's do x squared plus 5x plus 4. Let's show that this is.
Excuse me, Professor, could you go back to that last slide real quick?
Yeah, sure.
Thank you.
Sorry about that.
Okay, I'm good, thank you.
Cool. So we want to show this creature is big O of x squared. This shouldn't seem unreasonable. We're saying that the graphs of f and the graph of x squared should look similar when x is large. That's what we're saying. So if you were to go to Desmos, for example, it's always fun to do that kind of stuff. Let me we go to Desmos, let's just graph it. So let's graph two of these. We could take y equals, what was it? Was it x squared plus 5x plus 4? That's one graph. And then if we look at y equals x squared, so when I'm down here, it looks like they're separated. Right? But what's going to happen as I zoom out? As I zoom out and I move up, as you would imagine, when x gets large, these curves are going to get closer and closer together. Now, you might not believe it just looking at the picture, but if we made a table of values, suppose we did 100, 500, 5,000, and then we did the same thing for x squared. And we did 100, 500, 5,000. What you'll notice, look at it, the red curve is 500 larger when you plug in 100. When you plug in 500, the red curve is now 252,504. So now we're like a lot off, right? Seems as like. But what happens if we go a little further? What happens if we do 10,000? If you look at sole order of magnitude, they look pretty similar, right? When we start to round. And so what we're saying is, and if those of you who took calculus, as you know, or at least I tried to help you understand, as you know, when we took calculus, then when x is really large, the 4 is not contributing at all, is it? Not really. What is 5x contributing? Well, not much compared to x squared. And so the idea is, a generic way of thinking about this is, so the intuition. When x goes to infinity, x squared plus 5x plus 4 is approximately just x squared. Yes?
So in the previous definition, it says that the limit, when it goes to, it's less than or equal to a constant.
Correct.
What would the question be?
Well, okay, so that's what we want to find. Remember, we want to, so first off, that's a good question. The question that Abdullah asked is, in this definition, we said it's less than a constant. I am saying that this is equivalent to the definition we gave. The definition we gave is this. We have to find C and K to make this true. That's our job. Right now, we're looking for intuition on what they might be, right? But you're correct. If you do that, so we can use calculus to assist. So what is the limit as x goes to infinity of x squared plus 5x plus 4 over x squared? Now you might say, O'Grady, where are your absolute values at? But guess what? Do I need absolute values? They'd be redundant because all my numbers are positive. When x is positive, at least. So let's just do some basic algebra, things we learned in calculus. We can rewrite this thing. We know what the limit is. What's the limit here? It's just 1, right? So we know this limit is 1. If you've had calculus, maybe you have, maybe you haven't. If you haven't, it's okay. You don't need to do this. I'm looking for tools that we might have that can help us problem solve here. Now, here's the thing. These just give us some intuition and some sort of aid or what we might think. Our job now is to determine C and K such that x squared plus 5x plus 4 is less than or equal to c times x squared when x is greater than K. That's our job. We have to find C and K. So this is going to be a new thing for most of you. Now you might think because of your analysis that 1 is the correct choice for C, but it could be. So for each C, think about this. For each C, we're likely going to have a different K. No one said that there's only one C and one K. They sort of come as a pair. So when we went to Desmos and we took large values of X, we noticed that they were closer together, right? So what that tells us is, at least intuitively, that the smaller we want C to be, the larger K must be. Perhaps? But typically for these, especially with polynomials, is all you need is a little algebra. So here's a good way to reason. Here's one strategy. Let's assume X is greater than or equal to 1. Then we can say for sure that 0 is less than X squared plus 5X plus 4. And then remember what our goal is. Our goal is to show that this is less than a number times times X squared. So what I'm going to do is I'm just going to use very crude estimates. What is bigger, X or X squared? Well, I'm assuming X is greater than or equal to 1, so X squared is bigger. So I have this. And then I can replace, X squared. And then I can replace 1 with X squared. And of course, this is 10X squared. So C equals 10 and K equals 1 show that X squared plus 5X plus 4 is big O of X squared. That's one strategy. Yes.
How did you get 0 on the left side?
Oh, because they're all positive. I don't even need to do that, but sometimes it's nice to remind yourself of that. Everything's positive, right? If X is bigger than 1, then 5X is bigger than 1. That's a good habit to get in. If you can obviously show something's positive, show it. Does that make sense? And the other reason for that, why, then by putting that 0 there, guess what I don't have to write everywhere else? Absolute value. Because remember, the definition has absolute values involved. If something's positive, then absolute values are redundant. So the question was, how did I get, I don't know if you guys at home heard this. The question was, how do I get this? Well, again, X squared is clearly positive. But if I assume X is bigger than 1, then 5X is clearly positive. So you have the sum of 3 positive numbers, or non-negative. And then that allows me to not have to write absolute values everywhere. Now, there was nothing special about me doing it this way. There's other strategies I could have used. But one of the themes you'll see is the idea is to get replace these guys with the largest power. Or in general, replace all your terms with the function you're trying to get it to be big O with. So if you want to think about this in terms of limits, what is the dominant term in this expression when x is large? Well, for polynomials, it's the term with the largest power. So those are the guys we want to make everybody look like. Does that make sense? Maybe? I don't know. I mean, I hate to say, does that make sense? Because I know when I was trying to learn this years ago, I was like, what in the hell is happening? This is crazy. Does anybody have a question about this? Let's look at another way of doing it. And again, what I'm saying is, since C and K come in pairs, it is likely that no matter what you choose for your K, you can always find a corresponding C. That's sort of the strategy, right? So here's another strategy. This time, I'll assume that x is larger than, say, 10. Then, of course, once again, 0 is less than x squared plus 5x plus 4. Now, what can we say about these things now? What can we conclude? By the way, let me. Okay. Well, we know that the term we want to keep is x squared. We don't want this guy to go anywhere. What can we say about 5x? So maybe you do a little scratch work. You come over here and you say, okay, what can I say about 5x? So if I have 10 less than x, this tells me, for example, that 10x is less than x squared, right? And that tells me that 5x which we know is less than 10x, has to be less than x squared. So then I get this. This is completely fair reasoning. I can replace 5x with just x squared. Then what about 4? Well, it's the same reasoning shows that 4 is less than x. So what can we say then? Well, that tells us that 4, which is less than 4x, has to be less than 4x squared. So we can say that this is plus 4x squared. And so now this is 6x squared. And so once again, C equals 6, and this time K equals 10, show x squared plus 5x plus 4 is big O of x squared. So there's not just one way to do these. There's lots of strategies, and a lot of times it comes down to personal preference. How do you, the person doing the math, how do you like to reason? So if you study these examples, what you'll sort of come to terms with is that then you can classify things. So polynomials of degree n are always going to be big O of x to the power n. You just have to figure out how you can do it. It's not terribly difficult to do. Let's look at some other examples that are very useful in things like arithmetic and counting. So that was what, example 1. Number 2. Let's show the sum, k goes from 1 to n of k, which of course is 1 plus 2 plus 3, all the way out to n. Show that this guy is big O of n squared. So one way to think about what this is doing is this telling you how many steps it's going to take you to calculate this sum? Whether you do it by hand or you have instruct a computer to do it. At least, maybe we can get better, or I shouldn't say better, but oftentimes we're looking for the optimal big O. What is the best we can do? So how can we think about this? Well, one method so strategy 1 is I'm going to note that 0 is less than 1 plus 2 plus 3. And I'm going to use similar reasoning to what I did before. Each one of these guys is less than n. I guess I should be consistent with my n's. I'm using capital. Oh, that's ugly. You guys should fire me. Can I get fired? So each one of these creatures is less than n. 1's clearly less than n. 2's less than n. 3's less than n. And so how many copies of n do we have? Well, there's n of them, so this is equal to n times n, is it not? Which of course is n squared. So C equals 1 and K equals 1 gets the job done. By the way, sometimes we say that C and K are witnesses because they witness it. I think that's a funny term. So these guys verifies, no, verify. Boy, my. Whew. Fun times. Okay, now what would be another strategy? You might say, by the way, does anybody have any comments about this? Questions? You might say, well, we have a formula for that sum. Why don't we try to use that? And strategy 2 shows some interesting stuff. Since 1 plus 2 plus 3 all the way up to n, we know that this is n times n plus 1 over 2. We can reason as follows. 0 is less than n times n plus 1 over 2. Of course, this is equal to 1/2 n squared plus 1/2 n, if I rewrite it. And then we can reason that this is the same thing as 1/2 n squared plus 1/2 n squared. Now, why is this true? Well, this is true since n greater than or equal to 1 implies n less than or equal to n squared. And of course, this now equals n squared. Does that make sense? So it's just a different way to get to grandma's house. The only thing that changed from this line down was I replaced n with n squared, but I can do that because what's the smallest n can be? I mean, by context, n can be no smaller than 1, right? So then n squared is clearly greater than or equal to n. Anybody have a question about this? So just showing something as big O something else is usually a game. You have to do some scratch work, you have to do some reasoning, and then you have to put it all together at the end. So it's usually, as I said before with proofs, it's misleading when you read a book because it's not always clear when the solution's presented at first how the author figured out that solution. Sometimes it's direct from the definition, other times it's not. So the last one we'll do in this sort of group of examples is, and this is important as well, is that n factorial is big O n to the power n. So let's just prove this because it's very similar to the previous one. Zero is clearly less than or equal. It's not less than or equal to, it's less than. N factorial, which by definition is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And that is less than or equal to n times n times n times n times n times n, which is n copies of n. So that's n to the power n. So let me remind you again, why do we care about big O? The idea of big O is that when we have algorithms, it is a good way to estimate how many operations the computer is going to have to perform, or the human would have to perform. And so if you went and drew a graph of things like polynomials versus logs versus exponential, like I kind of sketched before, you will see that these things grow at completely different rates. Does anybody have any comments or questions? All right, well then let's stop there, and then we will move on next week. So please don't forget, if you have issues with the quiz, reach out to me. I'd be happy to discuss anything you might have. If you have any questions, let me know. Otherwise, thank you very much. And I will see you guys soon. Someone got a chat. What's up?